Solution equilibrium. We talked about equilibrium in terms of evaporation and condensation. Remember that? Dissolving a solute in a solvent is also an equilibrium process. So you have solute that's dissolving into the solution, but you also have solute that is recrystallizing out of solution. So if you have a sodium chloride and you put it into water, it will separate into sodium ions and chloride ions that are dissolved in water. That's what the AQ means. But these can also come together and recrystallize and reform the solid sodium chloride. So dynamic equilibrium happens where the rate of dissolution is equal to the rate of recrystallization. So here we have this illustrated. So here's a beaker, and we've got a crystal of sodium chloride in there. There are no sodium ions or chloride ions in the water, so no recrystallization can occur, only dissolution. So this starts to dissolve. As this starts to dissolve, now we have some sodium and chloride ions present in the solution. And they're just going to be kind of cruising along. They're not zinging like the gas ions do. These are just, they're kind of floating around in the water, literally floating. So they're moving around, and more of these ions are dissolving. But then as we get more and more ions in solution, when they just, through chance, bump into this sodium chloride crystal, they can recrystallize. So at first the rate of dissolution is faster than the rate of recrystallization. But the rate of recrystallization depends on how many sodium and chloride ions are in the solution. And so as it continues to dissolve, we'll get to a point where these two processes are equal. It's a dynamic equilibrium. If we have a saturated solution of sodium chloride, you could try this at home. It takes a lot of salt, so don't start with a big container of water. Start with a small one. You add sodium chloride, you stir it, it dissolves. You add more sodium chloride, you stir it, it dissolves. You keep doing that until at some point, no matter how much you stir, there's going to be solid sodium chloride at the bottom. You let that sit. That is a saturated solution, and it is in dynamic equilibrium. You have the solid solute in equilibrium with the dissolved solute. If you add more solute, it will not dissolve. This is a dynamic equilibrium, so it doesn't mean that everything's just fixed in place. There is dissolution and recrystallization occurring, but the amount of solid in there is staying constant. So that's a saturated solution. It's full. An unsaturated solution just has less than the equilibrium amount. That means if you add more solute, it will dissolve. Once you get to that point where it doesn't dissolve anymore, then it's saturated.
So in a saturated solution, the rate, they just keep dissolve and recrystallize?
In a saturated solution, you have dissolution and recrystallization occurring, but they're happening at the same rate.
And in the unsaturated one,
Dissolution rate will be higher. So in the unsaturated solution, you put more solid in, and the rate of dissolution is greater than the rate of recrystallization. You can also have a supersaturated solution. This has more than the equilibrium amount of solute. Does that sound impossible? Yeah, it does. And although it is definitely possible, it is unstable. It's hard to maintain a supersaturated solution. The way a supersaturated solution is formed is the solubility is temperature dependent. So if you heat the solution up, you can get a saturated solution at an elevated temperature where the solubility is higher. And then if you let it cool down slowly and carefully without disturbing it or thinking about it or looking at it, if you give it the stink eye, it might just start crystallizing. A little bit like our super cooled solutions that we did, where we cooled it below the freezing point and it stayed in solution, right? It stayed melted, it wasn't in solution, it stayed melted. And then you dropped a seed crystal in there and it all started to freeze. Same thing is happening with the supersaturated solution. So here are pictures of this happening. So this solution was made at a high temperature and allowed to cool. There's no crystals in there. We disturb this in any way. It's telling Bugs Bunny that he ran off the cliff. And then he starts to fall. Disturb it in any way, sometimes by touching it, by bumping it, by dropping a piece of dust or a seed crystal into it, and it will begin to crystallize. And then it will crystallize until it reaches a saturated equilibrium. So I have a couple of fun videos to show you about this. Let me get the lights here. So this is sodium acetate. Isn't that cool? Just put a stirring rod in there. That gives the crystals a place to start forming, and then they form on them, you know, they just grow and grow and grow. It's like so cool. Can we do that? Yes, actually we can. This is another one. This is fun with sodium acetate. These people are having a lot of fun. So just dipping toothpicks into saturated solution. It looks like pom-poms just growing. They call it hot ice. You see the temperature? 52 degrees. It looks like it's freezing, but the crystallization is an exothermic process, and so the temperature goes up. It gets hot.
Well, that's like when you, I've seen like a soda bottle or a beer bottle and get it like a certain temperature, hit it on the table, and then like instantly freezes.
I haven't actually seen that one, no.
You do Gatorade.
Can you?
Yeah.
I guess. Yeah.
I've had
you
them
could do that.
freeze. I've had them freeze when I took the lid off, because you reduce the pressure, and then they'll freeze. So here, using the saturated solution and making little sandcastles. Right? It's chemistry magic. That's harder to do than it looks. Although that would be easier than doing a big thing with dominoes, I suppose. In here they spelled ice. So the solubility of solids does depend on the temperature. For most solids, if you increase the temperature, you increase the amount that can dissolve. So things like, potassium nitrate, potassium dichromate, potassium chlorate. The temperature dependence for sodium chloride is pretty flat. As you increase the temperature from frozen water up to boiling water, the solubility of sodium chloride does not change much. And then there are some things like sodium sulfate where the solubility actually decreases as you heat it up. So it's very atypical behavior. Recrystallization is a technique that takes advantage of this equilibrium to purify a solid. So you've got a solid that perhaps you synthesized it, you made it in the lab, and you want to purify it. So It precipitates, and as it precipitates, it can include impurities, co-precipitates. We've had that happen in the lab, where a solid forms, like we were doing the copper and some of the magnesium, or this, it was zinc, I think, got stuck inside of it, and then it messed up our masses, right? So for ionic solids, you can do recrystallization. You take a saturated solution at an elevated temperature. One way to get that is you've got your solid and you've got it in water. You heat it up until it all dissolves. And then you let it cool slowly. What happens as it cools is the solid begins to form crystals. And as it forms crystals, the recrystallization that occurs, does so at a controlled pace so that it excludes impurities. So this isn't sodium chloride, but imagine that it is. Oh, I think it's table sugar. So as the sugar molecules come in here, they're going to line up with each other in a crystalline structure like those cells we talked about, in a way that maximizes the attractions, lowers the potential energy. And because there's plenty of time, and we've got dissolution and recrystallization happening at the same time, any impurities that might come in there are going to mess it up. And so they're going to be excluded. And so you can get a much purer crystal by recrystallizing it. Any questions? Making rock candy is something you can do at home too. I remember trying that as a child, and we didn't have the internet back then. So it was a miserable failure and wasted a lot of sugar. If you want to try recrystallizing sugar to make rock candy, I would encourage you to go online and find some good instructions for how to do it. Because it's not hard, but you have to have the right amounts and do it in the right way. And you can make very cool crystals like this. Gases dissolved in liquids behave differently than solids do. Solutions of gases in water are very common. Water that comes out of a faucet, whether it's the deionized water or the tap water, has gases dissolved in it, gases like oxygen. The solubility of gases in liquids decreases with increasing temperature. And our life experiences with soda can help us to understand that. If you take a cold bottle of soda and you pour it into a glass, you get some fizzing. If you take a warm bottle of soda and you pour it, there's a lot more fizzing, right? Have you experienced that? That's because the fizzing is caused by carbon dioxide that's coming out of solution. And so the solubility of CO2 in the warm soda pop is, he says soda pop, soda. I grew up saying pop. This is very confusing for me. The solubility of carbon dioxide in the warm soda is lower, and so more of it comes out, and that causes more fizzing. We also see that if you just have an open container of soda. If you have, say, and you could try this at home too, 2 glasses of soda, stick one in the refrigerator, leave one on the counter. Come back, I don't know, maybe 6 hours later or so, and taste them. The one that's left out at room temperature is going to go flat, lose its carbon dioxide faster than the one at a colder temperature. This affects fish and other aquatic life. Oxygen levels are lower in warm lakes and rivers. So if you have, say, a factory that's dumping water into a river, even if the water they're dumping out is perfectly clean, if it's too warm, it causes thermal pollution of the river. The area where the water's coming out is warm, the oxygen levels are low. Any fish that are unfortunate enough to be in that area are going to die because they can't get enough oxygen. This happened when we moved to Reedley and had some goldfish. And goldfish like cold water. And so we got a goldfish at the street fair and put him in a bowl, and he's like at the surface gasping for air. I'm like, what the heck is wrong with this goldfish? The water was too warm. I'm like, I am not running the AC at 72 all summer just for this stupid goldfish, right? So they can acclimate to warmer temperatures. They can get used to it, just like people can get used to lower oxygen levels living on top of a mountain, right? But you got to give them some time. So we would put ice cubes in there to gradually get the temperature up so he got used to it. The goldfish did not die because of that. I don't remember how that one died, but goldfish don't live all that long. Different fish are acclimated for different temperatures. Warm water tropical fish need a warm environment because that's what they're accustomed to. Cold water fish, salmon or bass or lake trout are accustomed to colder temperatures, and they will not live in a warm water situation. Pressure also affects the solubility of gases in liquids. So the solubility of a gas will increase when the pressure of that particular gas increases above the liquid. So cans of soda are pressurized, and the bottles are too. There's always going to be a small empty space above the soda, and there will be carbon dioxide under pressure there, and that's what gives you that sound, that psst, when you open it. That's the pressurized CO2 escaping. Once that happens, you've let out that pressure, the soda's going downhill after that. Carbon dioxide will continue to come out until it's flat. So why is that? Well, there's an equilibrium going on here. You have carbon dioxide in the space above the liquid, and you have carbon dioxide dissolved in the liquid. So you have carbon dioxide escaping and carbon dioxide dissolving. If we reduce the volume up here, which will increase the pressure of the carbon dioxide, we've essentially increased the concentration of the carbon dioxide. And that's going to cause the rate of dissolving to increase, because more of these gas molecules are going to run into the surface. And a new equilibrium will be established where the concentration of the CO2 in the liquid is now greater. That only works if you're increasing the pressure of the gas you want. They used to sell these things on TV where you could pressurize your 2-liter bottle of soda for people who have a hard time drinking a 2-liter bottle of soda before it goes flat. It would basically just pump air into it and pressurize the container. Well, that sounds really nice, but the problem is if you're pressurizing it with air, if I remember correctly, the percent composition of CO2 in air is something about like 0.6%. So if you pressurize it, are you really increasing the concentration of CO2 very much? No, you're not. It's not going to have a significant effect. If you pressurize it with CO2, then that will make it last longer. Okay? And you've probably heard of the soda stream machines. You can make your own soda at home. It uses pressurized carbon dioxide to carbonate your beverage. Okay? So if you pump carbon dioxide into the container, yeah, you can increase the concentration. Any questions? Of course, scientists, we like to quantify everything, right? We can't just leave it alone. So Henry's law gives us the relationship between gas solubility. Solubility is often given the letter S. Solubility of gas is equal to a constant times the partial pressure of that gas. This is called Henry's law constant, and you would look it up in a table. You do not memorize these things. So here, the Henry's law constants are given in molarity per atmosphere. So for oxygen, it's 1.3 times 10 to the minus third molarity per atmosphere, moles per liter per atmosphere. And so you would multiply that times the partial pressure of that gas in atmospheres, and that would give you the solubility. And there's a typo, that H is supposed to be a subscript. So let's do that. Determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. We're going to need the Henry's law constant. for oxygen. So 1.3 times 10 to the minus third. So KH 1.3 times 10 to the minus third, capital M per atmosphere. And Henry's law tells us that the solubility, here we're talking about O2, is going to equal to the Henry's law constant times the partial pressure of O2. Note that in this table, a temperature is specified. The Henry's law constant is going to vary somewhat with temperature, and so that's why the temperature was given. It doesn't actually come into the calculation, though. So here we have the partial pressure of oxygen. So that's PO2. And so we can calculate what the solubility of oxygen is. So the Henry's law constant is 1.3 times 10 to the minus third moles per liter per atmosphere. And the partial pressure is 0.21 atmospheres. And the units atmosphere cancel out. Where's my calculator? So we got 1.3 times 10 to the minus third times 0.21 equals. So my calculator is not set to display in scientific notation, so this is what it's showing me. What's the unit on that? Molarity, capital M, moles per liter. That should have two significant figures. So you could leave it like that. It'd probably be best to put it in scientific notation. 2.7 times 10 to the 4 minus 4 moles per liter. Any questions? Remember that capital M is moles per liter. Some of you or some of my other section are getting them mixed up with moles. Not the same thing at all.